Okay. So can you guys hear me? Can you guys raise your hands if you can hear me? Um, yeah, okay, great. Thank you. Gaurav, are you trying to speak and not able to because you just raised your hand, so I know you're there. Okay, Lara went to get that sorted out. In the meantime, I wanted to show you that the leaderboards are up, and many of you have been submitting, so that's great news. We have put a couple benchmarks on the leaderboards. The first is the best leaderboard submission from the team phase. So that's currently #1, so that would be a good benchmark for you guys to try to beat. The second one is further down here, if I can find it. Oh, it's currently at #25. It's the submission using just baseline deaths as a prediction. So, you know, that's a very rudimentary clinical only model. Obviously, we'd like to get it, see if we can use SNPs to predict and do better than that. And similar for leaderboard 2, we have the benchmark of the best submission from the team phase, but we don't have a clinical only model at this point. We do have Team Lucia, who is working on building a clinical model, who is not able to attend today, but they're working on that, and hopefully in 2 weeks' time we'll hear about their efforts, and hopefully we'll start seeing some submissions on the leaderboard from them as well. I'm hearing background noise. Is somebody able to speak?
Can you hear me?
Yeah, I can hear you now. Great.
Okay, great.
Okay. So with that, are you ready to start your presentation?
Yeah. Can you open up my slides?
I do have your slides open. Let me get my screen shared. Oh, all right. Are you guys, Gaurav, are you able to see my screen? I don't know what's going on.
Yes, I can see a lot of windows open on your screen.
Okay. Can you see your slides being presented?
Yeah. Yeah.
Okay.
So, should I just go?
Yes. So,
okay.
So we'll reserve questions until the end, but if you guys have questions, please raise your hand.
Okay, so my name is Gaurav Pandey, as Sauli mentioned, and I have been pestering a lot of you with emails about your predictions, so I'm guessing you know me from that venue as well. So I'm gonna just give a short introduction to how I'm planning to build supervised ensembles for the RA challenge, and we are hoping that this can become a methodology that we can apply to other dream challenges as well. I'm at the Icahn School of Medicine at Mount Sinai. My email is on the front slide too, but I'm sure you have it from my emails already. So next slide. Yeah, so I don't really need this slide here, but you know, a lot of us have experience with doing predictions of various kind in the biomedical domain, and you know, more often than not, we face challenges because these problems are really hard. And some of the reasons that you can guess for why this is because we have incomplete domain knowledge about a lot of these problems. we have a lot of data sources that are of varying quality, that are varying quantity as well. So we try our best to integrate as many of these data sources as we can. And then finally, the gold standards and the metrics themselves are unclear for performance evaluation. So all this leads to the kind of challenges that we have all been working on. So in Dream, in Innocentive, on Kaggle, basically we want to identify that if we are given a standardized set of data sets, a standardized problem definition, and a standardized evaluation methodology, can we identify the most effective predictor? So the team phase that you guys participated in was an effort in that direction. But an alternative approach to that, usually when people are trying to get as much of this within their own labs or within a small group, is developing ensemble approaches. So where we are trying to reduce our dependence on a single predictor by combining predictions from multiple predictors, right? And the goal is that by putting all these predictions together, we should be able to consolidate the good things in all these predictors and reduce the effect of the noise in the predictions of each individual predictors. So so that's what the ensemble methods aim to do. So next slide. Yeah, so this is the general view of an how one would think about an ensemble method. The original training data is given to you, based on which you can do like bootstrapping or sampling to create multiple versions of the data sets. Then on each of those individual versions, the D1 to DTs here, you can learn individual classifiers, which are then combined into this global ensemble classifier. Now, there can be a lot of variations on this figure. It doesn't have to be this way. You can create multiple classifiers on the same data set itself and then combine them, or you can create multiple data sets and learn the same classifier, let's say a decision tree on each of them, and then try to combine that. So a lot of ensemble methods have been developed that take various approaches to this problem. Next slide. Yeah, thanks. So a critical difference between the setup that I showed in the previous slide and the dreamy view of ensemble methods, as I, Gustavo, and many others like to see it, is this is the figure shown on this slide is a general overview of how challenges work. So base data is given to the participants for training and yes, for some testing as well. You guys have all these machineries on the left-hand top side for turning these base data into different prediction models using which you make predictions on the test samples. So these test samples, in this case, we are showing patients of two classes, but as in the drug toxicology case, this could be a completely different data set that we want to make a prediction on. So, and then the predictions that you make are then objectively evaluated, and then all the good stuff related to that we are able to accelerate research because we are parallelly working, many of us, and now as demonstrated by the community phase, we are now trying to foster collaboration in this particular model. But from the methodological side, the key difference is that compared to the previous figure where we showed this nice view of ensemble methods, now I, as an ensemble builder, don't have control over the various machineries that you guys are using in order to make predictions. So you might bring in different test data, different auxiliary data, for example, those that were provided for the RA challenge, in order to build a better predictor so that you don't just rely on training data. You might use methods that are prediction methods that are not typically used. So I think a lot of people are using not a lot, but some of you are using Gaussian processes. So those are, atypical prediction methods, but you guys are using them very nicely. So now I don't have really any control over how you are using this data. So now that brings us into this domain of what I like to call, this is not very commonly pursued area, but I like to call this the area of heterogeneous ensembles. So can we go to the next slide now? Yeah, so the most popular ensemble methods, some of you are already using them, like random forests and boosting, are homogeneous in nature. For example, random forests are all a collection of multiple decision trees, right? So you can understand a lot of properties of random forests based on this homogeneity. Similarly, in boosting, where you are iteratively training the ensemble model, there also in every round of training, generally you use the same base predictor. So in every round you learn a decision tree with different weightings on the training examples. Usually you don't see that you are learning a decision tree in one round, neural network in another round, SVM in another round, because then it becomes difficult to combine these in a principled fashion. So obviously, it's hard to say what the best base predictor should be beyond just trying, a lot of a lot of these base prediction models, a lot of these different features like you guys have been trying to do. But the idea that can be useful here is, instead of relying on these homogeneous ensembles which make assumptions on what the base predictor should be, how about just build heterogeneous ensembles that don't make an assumption on the type and the number of base predictors. So one team can be using a decision tree, one team can be using a neural network, or even they can be training their models on multiple different data sets, as they best think that their prediction model should be, right? So this is the scenario that we always encounter in dream challenges, that there is a lot of heterogeneity among the methods themselves. So how do we combine them? So I plan to take a different approach of building heterogeneous ensembles, for which there have been some methods proposed that there is scope for doing a lot more. So next slide. Yeah, so if you think about it, simple aggregation methods that have been used in a few previous dream challenges, and many of us use them in our routine work also. Just simple aggregation like mean, median, majority are all heterogeneous ensemble methods themselves, because they are not really putting a restriction on what kind of base classifiers these come from, as long as they make predictions on the same set of examples, right? So mean, median, majorities, majority voting has been studied a lot in theoretical terms and often works well. But there are a couple of I've shaded mean here because some of the results that we show you that I'll show you later on use mean as include mean as a representative of these simple aggregation methods, because that was working the best in the test that we did. A couple of more specialized methods for this are described. One of them is described on this slide. So this is the method of stacking, which in simple terms is simply the learning of a second level classifier, what is called a meta classifier, on top of the different base classifiers that you learn from the data, and they give you prediction. Sorry. So So everything starts with the train. Come on. So everything starts with, as in the dream challenge. Oh, come on. Guys, sorry. So 1 second. Yeah, sorry, bad timing. Okay. So everything starts with the training data, as it starts with in our RA challenge. Then, the example used here is to bootstrap from the training data, create multiple versions, and then you learn what can be called tier 1 classifiers. So all the predictors that you guys are building can be framed as, all these numbers here, C1, CT minus 1, CT, CT plus 1, the numbers don't really matter, uh, but basically each one of you will fit into this into a slot of these tier 1 classifiers, or I should say the predictors that you guys developed in the first phase, in the team phase. And then a meta classifier is learned on top of this. We often use logistic regression, but I aim to go a lot bigger than that and test out many different meta classifiers, which will give you a final prediction. Next. Yeah, but then there are a couple of selection-based methods also. So you're given this collection of, in our case, we don't have such a big collection, but you can imagine if you are going to aggregate all the methods that were submitted to, a big, a dream challenge where there were a lot more participants, then I may have let's say 100 base predictors, of which I may only want to keep 20 of them because the other 80 bring down my performance in terms of overall predictability, just because they don't have as much signal as the 20 good ones. So these kind of methods basically focus on identifying that subset of the whole set of base predictors that can give me the kind of predictability that I want. So you can imagine, if you were to develop such an algorithm, the basic idea you would have is, okay, let me do a greedy selection. Let me start picking up base predictors in terms of how well they perform individually and combine them into an ensemble until the performance doesn't change. So I add 1, then 2, then 3, then 4. And I'm not really caring about, how complementary or how redundant all of these base classifiers are with each other. All I care about is my ensemble's performance should keep increasing. So that's why we call this the completely greedy selection approach. But then Rich Caruana had a couple of nice papers on a more, it's still a greedy approach, but it's a more thoughtful approach where every time where you start with a small set of base predictors, and then you add a base predictor at a time, and the condition for the base predictor selection is that it should increase the performance of the current ensemble. So what that means is that the new classifier, that new base predictor that you're adding, may be diverse from the current ensemble, and that's why it leads to better prediction as a whole with the ensemble. And it may not by itself be a very well-performing classifier. So this is a difficult point to make during this talk, but we have some results on how we where we actually demonstrate that this CES approach often alternates between picking up smart classifiers on their own, but then also classifiers that are complementary with the original data set. So with the original ensemble. So I cannot go into that, but I hope you understand the basic idea, or I was able to explain that. Next. Yeah, so in a paper in IEEE ICDM last year, Sean Whalen and I did kind of a comprehensive evaluation of a lot of these heterogeneous ensemble methods. The citation for the paper is below, but feel free to ask me questions by email or ask for the paper itself by email. We had 4 different data sets here, which related to predicting genetic interactions and protein functions from genomic data. But for the purpose of this talk, you can think of it as any single data set given out in a dream challenge. So it's these are hard problems of a similar nature. So I won't go into details of these too much. So next. Yeah, so but I want to show you results on what we get. So for these 4 classification problems, the number in bold is what you get by stacking aggregated. So I have completely skipped over. Actually, I should explain this. So what we did was we created our own ensemble by 10 bagged versions. So we are doing the same bootstrapping to the training data, and for each of those bootstrapped versions of the training data, we are learning 27 different classifiers. So these include decision trees, these include neural networks, these also include random forests and boosting, which you can use as a base classifier itself. And the total collection of these 270 base classifiers is now used to build ensembles. One important point to note here is that we don't have separate training and test data sets. So we are being very careful about using not only cross-validation, but in fact nested cross-validation in order to make sure that there is no leakage of labels across any of this. This did make the methodology more complicated, but it was worth doing it in order to explain, in order to investigate these methods. So these the numbers shown in the table carry a lot of information. So I'll emphasize the most important ones. So the best base classifier that is in the first row for all these problems turns out to be either random forest or boosting. So we know that these homogeneous ensembles, as we call them, do perform well among the best among all of them. Oh, one more thing. These are AUC scores. So, but we tested this using precision recall metrics, and we pretty much got consistent trends. Then, if you look at mean aggregation, that's the second row. Usually, you don't get as good performance as the top base predictor, which is an indicator of the fact that that there are actually in this collection of 270, there may be 200 of these base classifiers that are actually bringing the performance down. So we do want to either weight them as stacking would do, or do a selection of them as CES would do in order to make more effective ensembles. And these performance metrics are shown here. So in all the cases, stacking aggregated, one of the versions of stacking that we use. So by aggregated, what we mean is that there are 27 different base classifiers, 10 versions of each of them. So what we did was, before we put them through stacking or put them through this meta classifier, we averaged the predictions of each of those. So 10 decision trees turned into one aggregate decision tree, then 10 neural networks merged into one aggregate neural network, so on and so forth, and then we put them into stacking. So because we are using this structure within the base predictors themselves, we are able to get better performance than any of the other methods. But in all the other methods, pretty much all the other heterogeneous ensemble method, you can see an improvement over the best base predictor, which should be a good sign for building a heterogeneous ensemble. I agree that the performance varies, how much advantage you can get, and these things you can only test by, actually doing them. There is no theoretical guarantee of getting an improvement. But because we have these consistent results that these heterogeneous supervised ensembles can actually give you a boost over what the best base classifier, or in the dream challenge scenario, what the best is. We were interested in in this RA challenge, which is why I was invited to join this team. Is we want to see how far we can get. So next slide. Yeah, so let me summarize what we are trying to do here, and I still have some way to go before I can show results for this. So the goals of this particular component of the community phase are twofold. One is investigate ways of assimilating predictions that were submitted to the team phase. We just want to do an investigation, whether supervised ways work, maybe they don't work, are there any particular issues that lead to them not working, and so on and so forth. Then, as Lara has and others have communicated in earlier emails, we want to use this as a solid benchmark for you guys for the community phases, so that all these algorithms can only do so much, but we are confident that when you guys all put your heads together, then you will be able to actually beat whatever benchmark we can produce by this approach, by virtue of the ideas that you guys are going to try. So we want to set this up as a benchmark. And one thing that I personally, and I'm sure everybody here is on board with that, is that this will not be a competing entry in the challenge. That is, it's not like this will, some of the entries from here will be on the leaderboard, but those will be for benchmarking purposes only. So don't think that I'm trying to win the competition just by using all the hard work that you guys have already done. So this is purely a scientific exercise, and all the credit to winning the competition or doing the best in the community phase. Everything will go to you guys. So let's come to the logistics of this. You have already been hearing a lot from me about this. So I'm trying to make these ensemble methods for both sub-challenge 1 and sub-challenge 2. I already asked for leave-one-out training, leave-one-out cross-validation predictions on the training set, which I'm going to use for the training phase of these supervised ensembles. So, in stacking, in ensemble selection, all of them need some way of figuring out, with respect to the true labels, this combination of base predictors is the best. So far I have received 10 predictions for for sub-challenge 1, 7 for sub-challenge 2. Now, once you have trained these leave-one-out trained ensembles using these LO predictions, I need to apply the model to the test predictions as well, right? No labels of the test set will be used, but I need to apply them, which is why it is crucial for me to have the same number of test predictions as the training LO predictions. If that is not the case, my only option will be to drop predictions from the training, drop some of these LO predictions just because I don't have their test predictions. And given that we only have 10 to start with, or in the second case, we have only 7 to start with, that will not be a desirable thing to happen. So I really urge you, if you haven't done so far, please submit your test set predictions to the Synapse projects I've already emailed you guys with. But if you have questions or concerns, please get back to me. We really do need, I want the numbers on all the rows to be 10, 10, 10, and 7, 7, 7, if not more. So if you haven't done it already, you might just have to locate what was your best test prediction, you must have submitted these test predictions to the leaderboard, that is the held out training set leaderboard and the final corona test set leaderboard. So all you have to do is dig up where that particular model is, generate predictions, or you may already have predictions or the files for them, and just submit them at the Synapse projects that I sent you. I really would be thankful for all of you. You have been very thankful, very helpful already. But if you can submit the rest of these predictions as soon as possible, then we can proceed and then add a little more punch to our community phase. So that's pretty much the end of my talk. Can we go to the next slide?
So can I make a comment really quickly?
Yes.
So we do have all of your submissions to the leaderboards and to the final scoreboards. It's impossible for us to know which ones correspond to which cross-validations. So that's why we need you to submit this again. And failing that, if you can't find the actual files, if you know what they correspond to in the leaderboard, which models correspond to which cross-validations, we can download those as well. So it's probably easier for Gaurav if you upload the file to him directly, but if all else fails, let us know which leaderboard submissions your cross-validations correspond to, and we can dig them out of Synapse if that's the easiest way for you. All right, Gaurav, you're back on.
Yeah, so I just want to end by thanking all of you for participating in this team phase as well as in the community phase, and showing support for this, at least the part that I am doing. I know you guys are doing a lot on your own. We'll hear about that, but I also want to thank Gustavo and the folks from Sage Bionetworks, especially Lara Soli and Abhishek, for helping me, bringing me into this effort and then helping me with it. And finally, Sean Willen used to work with me, who did a lot of the testing and the experimental work that I showed you earlier. So yeah, so a lot of things have been happening in this particular direction, and we hope with your effort, a lot of things will keep happening. So that's it. Ready to take questions.
Great. So thank you, Gaurav, for that presentation. If anyone has questions on that presentation, feel free to raise your hand now, and I'll unmute you. No questions. I'm surprised. All right. You must have done a really good job of explaining.
Maybe a really bad job. So yeah, so feel free to send me any questions related to this or anything else. And then once again, please submit your test set predictions as soon as you can, so that things can proceed in this direction. So yeah, thank you. I'm done.
Great. So since no one has questions, let's proceed to the presentations. It looks like Team GSTM has, each of the 4 component groups have submitted their own set of slides, so we'll just go through one at a time. We'll start with Team Tracy since I have it open first. Let's see. Oh, here you are. Yanfeng, are you presenting for your group? I've unmuted you. Can you, are you there?
Hello. That's not my group.
Oh, I'm sorry. That's Tao Wang. Sorry about that, Tao.
Oh, okay. Can you hear me now?
Yes.
Okay. So I only have one slide to present. So during the past about 2 weeks. We try to install multi-blob. However, it takes too much effort to install the current version of LDAK, which implements the multi-blob. The current version of LDAK is LDAK 3, but multi-blob is not formally implemented in LDAK 3 yet. So we will need to wait for about 3 weeks for the newest version of LDAK that formally implements multi-blob, and we will try multi-blob. Yeah. And the second thing is that we try to look at an online database called CADD. So this database gives each SNP a broadly applicable metric that can help you weigh and integrate diverse information to prioritize your research. And the score is called C-score. So I try to delete. I have a list of 124 SNPs for my prediction model. So I try to delete the SNPs that have higher C-scores, which is larger than 1, from the model. So I deleted a total of 11 SNPs from the model which have C-score larger than 1. And that seems to improve the prediction according to my own cross-validation. However, when I submit that to the leaderboard, it does not change the prediction much. So that's the second thing that I tried. And a third thing that I tried is I tried to drop. Okay. So for both sub-challenges, I have 5 submodels, and I aggregated the 5 submodels to give the final prediction. So I try to drop each one of the 5 submodels for the 2 sub-challenges, and to see whether that can help us improve the prediction performance or not. So what I found out is that when I drop the 4th model, the AdaBoost model, for the second sub-challenge, it can improve the performance of the prediction accuracy according to my own cross-validation. However, it does not work on the leaderboard either. So so that's what I've got so far.
Great, thank you, Tao. So now we'll go to Guan Lab, and let me unmute you, Yanfeng, this time.
Okay, great.
There you go.
Okay. Based on previous discussion, we saw that using biological networks to drive SNP discovery might be an excellent idea to try. So next slide. So my group actually has some expertise in this field. So as you can see, this is a previous benchmark study. So Group C is now they become very famous, the GeneMania algorithm, and they perform the top in cross-validation. And Group D is our group. Our method actually performed the top in the new, previously unseen test data, just like what has been done in the DREAM challenges. So I think the quality of our network is, I guess, pretty good for this task. So next slide. So our network has previously been used to detect many genes involved in complex diseases such as BMD, bone mineral density, male fertility, and also pain-related genes. So this is just one example of a very recent paper that used our network to drive novel disease gene discovery. So this network is primarily used by the mouse genetics community, and now we will have to deploy it in humans for the RA challenge. So next slide, please. Next slide, please. Thanks. That's it. So, okay. So we have some updated work on this network field, and we recently extended our networks to the splice isoform level. And so we tried this TNF, which is a critical gene in the RA, and and we extract the local networks of this gene. Next slide. So as you can see, many of the genes that are directly related to TNF, as predicted by our network, are involved in immune-related biological processes, which we think are potential causal genes. Oh, no, sorry, not causal genes, potential genes that could be used to identify the SNPs for the community phase. So so far, we have write some code to map the genes to SNPs through the using the NCBI web page. Next slide. Oh, actually, we have a small kind of technical difficulty here. So after we map the genes to the SNPs, we found that many genes have hundreds to even to thousands of SNPs. So there is still some difficulty in narrowing down this SNP list. So the future work of next 2 weeks is we need to write some programmatic tools to retrieve the eQTLs. We're still trying to figure out what's the best way to do it. And we will test the expanded SNP list. Sorry, it should be list, not set. Oh yeah, set is okay. So we should test this expanded SNP set identified from our network in the leaderboard. Next slide. Oh, just a small acknowledgement. So Fanju, he wrote the code for processing the NCBI SNP list, and Hongdong Li, my other student, he generated the network for us to retrieve the TNF interactions. And also, as you can imagine, that there are some discussions going on within the GSTM larger group, and we got many insightful inputs that kind of guide our future directions in this RA challenge. Thanks a lot.
Great, thank you. So,
oh, questions?
Does anyone have questions for Yongfeng?
Oh, we're already muted.
Okay, so next we're going to go to SBI Lab. This is you, right? All right, sorry guys, my usually view these full screen. I'm not seeing it, so I'll make it as big as possible. And Javier, can you?
Yeah, I'm here. Can you hear me?
Yes.
Good. Well, I have to say that in the community phase, the work is mainly done by Daniel Aguilar, but this week he's on vacation, so I will do the presentation for him. So as we explained at the beginning of the community phase, we would like to focus in the selection of SNPs, and we are working on it. Can you go to the next slide, please? One of the things that we wanted to do is, as in the team phase we splitted the patients by drug, now we thought that we could split the patients not only by drug, but also by if it takes methotrexate or not, and in the level of baseline DAS that they have. And can you go to the next slide, please? So taking all these factors to categorize the data or divide the data, we have 25 combinations of treatments and baseline DAS, and we have calculated the associations between each SNP with any of those combinations, with the response of the patient responding to the treatment or not. And these are the 25 combinations that we have tested. Can you go to the next slide, please? And the other part was to use our lab tools just to reduce the number of SNPs. As we commented, we just selected all these SNPs that belong to a protein in the encoding gene or within the boundaries. We also scored these SNPs using our Guild software that uses an algorithm that is called NetScore. And in difference with the team phase, now we are using the network of Reactome that is for that includes metabolic networks. And these are the numbers of the reduced number of SNPs we obtain. So at the end, with this selection, we end up with a list of 9,000 SNPs, approximately. Can you go to the next slide, please? And yeah, this is just a summary of the some previous slides that why dividing the patients by the treatment they are taking can be important because, for example, in this case, if we take just this marker, if for all patients the p-value of the association is very bad, but when the patient is when it takes adalimumab and methotrexate, the p-value of this association is bigger. So this could be a good candidate for this group of patients. Can you go to next slide, please? Yeah, and just we are finishing the analysis with NetScore, Guild, etc. But for this statistical association using the Fisher exact test, we have already uploaded all these results to the Dropbox that we are sharing in our group. And in this Dropbox folder, you can find this file with all this information. Just if you want to test your models with the SNPs with better p-values. Yeah, and that's all.
Great. Sorry, Anna, I missed you that you had a question for GuanLab. First, does anyone have any questions for Javier? All right, Javier, I'm going to mute you, and then Anna, I will give you a chance to go back and ask your question. Go ahead, Anna. Can you, are you able to speak? It looks like you might be muted on your end.
I think I'm able to speak. I just had a quick question for the GuanLab presentation. The network, I quickly checked the network paper that was mentioned, and it looks like it's it was done for mice, and the mouse funk analysis was also done for mice. So do you have a complementary network for humans that you've mapped through orthologs or something like that, or is it the network that you used was the mouse network?
Yes, we do have a network for human. Actually, we did a pretty interesting thing. So for human, as you know, in public databases, there are a lot of cancer data. So this data tends to drive the whole prediction towards some cancer-related genes. So for human, we have two networks. One is integrating all data, and the other one is integrating only data without cancer, so non-cancer data.
Do you have that network available somewhere?
Yes, I have it somewhere. Should I type it through the should I type the web address through somewhere on the webinar, or should I?
Why don't you just email me and I will send it out, or email me or Laura or whoever's email address you have available, and I can distribute it if it's just a web link.
So actually, I would expect this human-specific network is even more accurate than our previous mouse network. We have done a lot of tuning on it, although we haven't been able to publish it yet. So
did you compare? Did you compare it to like multinet and HumanNet and all the networks that have been coming out of Harvard recently?
Coming out from where?
Harvard. I think, or actually HumanNet, I think was from multinet was from Mark Gerstein's lab.
Oh, I see. We didn't compare that. I only compared to my own network.
Okay. Okay, thank you. It would be great if you could share it. Thank you.
Yeah, of course. That's not a problem.
Great. Thank you both. So next we have Team MI. And hang on a sec while I unmute you, Lou. Lou, are you there?
Okay. So can you hear me?
Yes.
Oh, okay, that's great. So we have modified our prediction method customized to be drug specific. So basically, previously we just take the whole SNP set and then predict for all patients. But now we are trying to make the predictions drug specific. And then we repeat the experiment on other teams' experiment SNP sets, and now these are the results. So this is prediction method is by gamma, and then in sub-challenge 1, on the leaderboard the predictions 0.5 and 0.48 for SBI and SBS SNP set, and then 0.47 for Tracy SNP set. So these results are very similar to the previous results, although a bit, maybe a little bit lower, but then they are really similar. And then for sub-challenge 2, it's still the same. So we can from the result we can say that actually the methods are very similar there, and the key part is like the SNPs here. So if we select a good SNP set, then the prediction will be there no matter what kind of prediction method we are using. And the cross-validation result is very similar to the leaderboard result. Yeah, but usually the cross-validation is higher than the leaderboard result. But then for the GuanLab SNP set, it's a bit strange that they have lower prediction accuracy in the cross-validation, but then they have high performance in the leaderboard. We don't know why it is like this, but this is kind of interesting. Could you go to the next slide? Hello, could you go to the next slide? Thank you. Okay, so that's basically the other experiment we have done, and then we think that HLA imputation will be important in the future case. So we want to because HLA region is very related to the autoimmune diseases. So we want to impute that impute the SNP data for that region, and then the software is there. But then there is problem with installing the software, and we have some colleagues who are working on this, and it seems that installing the software is too complex. And the things that also when you impute the data, you need the expertise to do this. So we hope that the organizer can help us with this. So, and then if you impute the data, then it can be shared across all groups. So that will be a really nice new data to work on. And the next plan is like we use some new test. So previously we always use GWAS. So it's like one phenotype, one SNP and one phenotype testing. So now we are using single SNP and multiple phenotypes testing. So it's based on CCA idea. We have some colleagues who have a method about this. So basically, we can test one SNP and then test one SNP against the multiple phenotypes here, and then we hope that we can get some promising result from this, and we will share this with other teams in our group. Okay, that's all for today. Thank you. Is there any other questions?
Okay, Lou. So I haven't worked with this HLA imputation software, but I do recall from the presentations that Team SDSI did some work in the HLA region, so that might be a good approach is to join forces with or ask Team SDSI.
Okay, thank you.
So does anyone have any questions for Lou? Okay, Eric Kramer from Team SDSI is next, and I understand you don't have slides, but can give us a verbal update. Eric, are you there?
Yeah, I'm here. Can you guys hear me?
Yeah.
Okay. Yeah, so two quick things. With regards to the HLA typing, we used a program called HiBag. It's just an R package, and it uses a random forest to impute HLA types. And it actually has better performance than HLA input, or HLA impute, which is, I think, what you linked to there. So you guys can check that out, or we can just send you the HLA typing themselves. And then I think the Guan lab mentioned mapping EQTLs to SNPs. So we also have that. So we use this program called Matrix EQTL, which both tests for EQTLs and then is mapping them simultaneously to genes. And so we have a lot of data basically mapping EQTLs to gene expression in genes. So we can share that with you guys if you're interested. But so overall for our team, we've kind of divided the workload. So Team Linked Open Data has been focusing on kind of collecting features that can be used for input into the model. So they've been using known SNPs associated both with rheumatoid arthritis, and they've pulled down SNPs that are associated with other autoimmune diseases. The thinking here is that maybe these patients have some sort of comorbidities that are kind of expressed by these SNPs also. Team Linked Open Data has also collected various EQTLs using the EQTL browser provided by NIH. So we have all of those. That's what they've been doing. And then Team Outliers has kind of been working on better modeling. And so Team Outliers looks like they're getting pretty good response by using generalized linear models. Specifically, they're using a gamma distributed response rather than the standard normal response. In addition to that, they're using end DAS rather than delta DAS as their predictor. So basically, the theory here is that we can go ahead and regress end DAS against baseline DAS, take the residuals from that model, and then try to predict on those residuals. And so making some progress on that front. And then the final thing is that what I've been working on is sort of using measures of heritability as a kernel for kernel methods. And so we haven't had very much luck picking out individual SNPs and using them as a model. So instead of doing that, what we've been doing at SDSI is taking about 100,000 SNPs, using those SNPs to create sort of a relatedness matrix, and then using that matrix as a gram matrix for kernel methods. So we've seen a little bit of an improvement, but the method's not quite done yet, and we haven't made any submissions to the leaderboard. So that's what we've been doing on our team.
Great. Anna or anyone else from the team want to add anything? All right, Anna, let me unmute you. You're unmuted.
Hi, so I just wanted to clarify that, yes, I wanted to clarify that our modeling is just to make sure that the outcome that we are all predicting doesn't have too many confounding variables. So if we are finding SNPs that are associated with the final outcome, that outcome is somehow can be predicted by SNPs and not just a byproduct of the baseline. So what Eric has mentioned was correct. We have produced the residuals from the gamma model, and we have those residuals available if anybody is interested. But that using a linear model of drug, methotrexate, gender, and age, just the clinical seems to have. The previous correlation of the same kind of model was about 42%, and using the correlation, predicting the residual is about 46%. So that's one of the things that we have. It's a different, it's function of the outcome if people want to try to be predicting that. Another thing that we are doing is building deep belief networks with Dropout to try to predict the outcome, and that's taken quite a bit of time, as you can imagine, but we're making slow progress towards that, and we'll need about 1,000 SNPs or so that we are curating through the process that Eric has mentioned, and we will try the models on that, and I will report as soon as those models are done, which should be in the span of the next 2 weeks. That's our expectation, optimistic expectation.
Great, thank you. Anyone else have any questions or anything to add? Okay, so Team Lucia is on holiday at the moment, so they're not able to present on the update for their clinical model, but hopefully we'll see some submissions to the leaderboard soon, so you'll have some good benchmarks against which to measure your clinical plus genetics models, as well as to incorporate into your genetics models. As for our plan for, we do have a webinar plan for 2 weeks from now. Our current plan is to look at the state of the leaderboards and see how you're doing relative to benchmarks. But if anyone has any suggestions or topics that they think would be helpful to cover, we would love to hear them. So if you have any suggestions, anything we can do, any presentations we can put together that will help you. Otherwise, we'll just give you a chance to present, as well as to look at how the leaderboards are faring. So anything you can do to get your models progressing and getting submissions to the leaderboard in that time frame would be great as well. So let me give you a chance. Does anyone have any last questions or comments before we sign off? All right, Gaurav, you're unmuted. Go ahead.
Yeah, so I just wanted to repeat one last time. Please submit your test set predictions, because I won't be on the next webinar. So, and I don't really want to spam you guys again. So that's all.
All right. So we'll be sure to remind them next webinar if you're still having problems, Gaurav. With that, since I'm not seeing any other questions, I'd like to thank Gaurav for his presentation, and thank all of you for your presentations, and keep up the good work. Thank you.